Starting with Robert Morris, who is an English-Brazilian mathematician at IMPA, professor at IMPA at the Instituto Matemática Pura e Aplicada, and has been here for several years. Although he got his PhD only recently, he has had dozens of papers, over 40, almost 50 papers on difficult top topics. He's an expert on extremal and probabilistic combinatorics, but also on percolation, bootstrap percolation, graph processes, and even number theory. So let me ask Robert to give the first half of this double act. Please.
Thank you. So thanks Bailey for the introduction. It's a great honor, great pleasure to be here, to be speaking real. Oh, no, I don't. Can you hear me? I'm going to tell you about this method of hypergraph containers. Before starting, I'd like to say that this talk is all based on joint work with our brilliant co-author, Wojciech Samety from Tel Aviv University. He's really, for those who don't know him, a sensational young mathematician, had an enormous impact on this work, on the area. So for those who don't know, I encourage you to check out his work. So this is his formal picture, and he gave me permission to show you also this one of us working on containers on the beach. That's my job. This was a few years ago. Anyway, so I also would like to, before I start, give credit to David Sachs and Andrew Thomason, who independently discovered the things I'm going to be talking about at the same time. Kleitman and Winston, who several breakthrough works, in particular one that very strongly influenced us. Sapojenko, who developed a general theory of graph containers, which we generalized to hypergraph containers. And Conlon Gowers and Schacht, who proved some wonderful results. So 2016 is a bit inaccurate. These things appeared around 2009 and appeared in Annals finally in 2016. And this gave us the motivation to generalize the things to hypergraphs. So I'll mention some more names in a few minutes. I really want you to take this the idea that we're building on this enormous body of work that's been developing over several decades in combinatorics with many extremely important breakthroughs. So this is just the next step in a very long-going project for the community. Okay, so what are containers? What kind of problems are we looking at? We're looking at things like counting, say, triangle-free graphs, or maybe looking at the largest triangle-free subgraph for a random graph, or perhaps looking at sort of what the typical triangle-free graph of a certain density looks like, or maybe trying to prove that so much exists by picking something randomly and showing it has some certain properties. These are very sort of disordered objects, and yet one sees that sometimes putting certain conditions on, order appears out of the disorder. So I'll try to, so the example I just mentioned was triangle-free graphs. I'll focus on that example in the first half of the talk and try and give you some idea of what containers are and what these container things look like. In the second half of the talk, József will, it turns out these things apply to a vast array of different finite objects. And József will just give a few sample applications to sum-free and arithmetic progression-free sets, and a sort of surprising construction in discrete geometry. But really there are sort of dozens and dozens of applications in different areas of mainly extremal and probabilistic combinatorics, but also we're now branching into other areas. Okay, so I don't know exactly how much to expect from Jonas's knowledge of extremal and probabilistic combinatorics, so I thought I'd tell you just a tiny bit of history of extremal graph theory. So it started with more than a century ago, Mantel proving this very sort of simple, beautiful theorem that a triangle-free graph on n vertices has at most n squared over 4 edges. It's sharp because you can take a complete bipartite graph. Turan generalized this to complete arbitrary complete graphs. Edish and Stone looked at the graphs avoiding an arbitrary non-bipartite graph. This problem sort of, okay, things were discovered many years ago, but there are still many, many interesting and difficult open problems, particularly for avoiding bipartite graphs. So, this is just to give a very brief bit of history. So we'll be interested in this first half of the talk in looking at Mantel's theorem, instead of looking in the complete graph, looking in the setting of a random graph. Okay. So what's the definition? So we take the random graph GMP, which means we take n vertices, and for every pair, we toss a coin independently and put the edge in with probability p. This gives us a distribution on all graphs that we think of as being a single random graph. The extremal number of a graph H inside this random graph is just the maximum of edges in a subgraph that avoids this H. You think of H as being a triangle. And I want to talk about proof of this theorem. So first proved by Frankel and Rödl in the 80s, Haxon, Koyakawa, and Wuchak give a sharp-bound but also generalized this in the 90s. So what does this say? This says that if you take the random graph, you take the largest triangle-free subgraph, you keep about half the edges. This is if p is bigger than 1 over root n. This is the lower bound is easy. You just intersect your GMP with a copy of the complete bipartite graph. With high probability, you keep half the edges. The lower bound on p is also sharp for also quite simple reason. So the difficulty is proving the upper bound for these values of p. So one of the reasons this gives me a nice opportunity to mention several of the names who were very influential in popularizing these kind of questions and in developing the field in the 80s and 90s. So in particular, Koyakawa, Wuchak, and Rödl wrote some further very influential papers, and also Rödl and Machinsky wrote some very influential papers on similar problems for Ramsey questions. Okay, so how might one go about proving such a theorem? So one thing you might try to do as a first idea, you might try just calculating the expected number of triangle-free subgraphs with this number of edges. And if it might be small. If it's small, you're done, because you just use Markov's inequality. If the expected number is small, with high probability there are none, hooray. Unfortunately, it's big. So this idea doesn't work, so we go back to the drawing board. So why did it fail? Why is this expected number big? So what do we do now? Let's look at why we failed. Well, these triangle-free graphs on M edges, they're kind of clustered together. So we fail just because the complete bipartite graph itself has way too many triangle-free subgraphs with M edges. Just one, just the complete bipartite graph, already you're dead. But the complete bipartite graph itself isn't really a problem. You can just deal with it separately. So maybe, sort of hand-wavy idea, maybe these things are just clustered together, sort of subgraphs of bad graphs. Maybe we can understand this clustering, deal with these bunches one at a time, and then maybe we're happy. So more precisely, we'd like to prove the following container theorem. So we'd like to find a collection of these bad graphs with the following properties. We don't want to have too many of them, because we're going to want to take a union bound over them. We want to be able to say something about them, so maybe they should have few triangles. And we want to cover all of the triangle-free graphs. So we're going to partition, or not quite partition, cover the triangle-free graphs with these special containers. Each one will contain many of subgraphs, each one with few triangles, and hopefully there won't be too many of them. And that's what containers essentially are. So what do I mean by small and what do I mean by few? Well, it's not actually too complicated. So few, in order to say anything really strong about these graphs, we'd like it to be little o n cubed. So n cubed triangles in total, that could be a little lower for that. And if we want to be that small, to have that few triangles, then we can't really do better, roughly speaking, than this bound n to the 3 over 2. It turns out this is about as well as you can hope to do. And this is true. Okay, so suppose one can find such a nice set of containers, then, okay, what does one want to do with it? How do you deduce the Frankel-Rödel theorem? Okay, sorry, so we call these containers. So we're going to deduce the Frankel-Rödel theorem, which was the extremal number of the triangle in GMP is about density half. So it's essentially the complete bipartite graph, essentially intersection with the complete bipartite graph, by taking a union bound over containers. So instead of having about 2 to the n squared containers, now we only, so graphs in total, now we've got the number down, so the union bound's not so bad. And now it's enough to we can deduce it for each container one at a time using Chernow's inequality. And this n to the 3 over 2 that appears in the exponent is intimately related with this n 1 over root n in the theorem. N to the 3 over 2 times root n is n squared. So that's for the relation between them. So what's the supersaturation theorem? So we need to be able to say something about these containers. We know they contain few triangles. So what we use is this classical supersaturation theorem for triangle-free graphs that says that each of these containers, it has few triangles, and therefore it can't have too many edges. So remember, Mantel's theorem said a graph with 0 triangles has at most n squared over 4 edges. This says you can still have quite a lot of triangles, but if you're little o n cubed, you've only got a few more triangles, little o n squared more than the minimum. So this allows you to easily deduce the theorem I stated before. But the calculation is, maybe it's 10 lines, so it's too much to tell you, but I mean, if you go home and try and do this, then you'll probably succeed. Okay, so how does one go about proving a container lemma, a container theorem like this? How does one find a collection of graphs with these nice properties? So perhaps the key idea is not to work in the family of graphs or triangle-free graphs, is to work in a more general setting of hypergraphs. And so let me tell you the key hypergraph lemma for 3 uniform hypergraphs that implies the container theorem I just stated. So, okay, so given every C there's a delta. So we have a 3 uniform hypergraph, so that's a collection of triples on vertex set 1 up to n, say. It's got average degree d, so on average a vertex is in d of these triples. And we want the edges to be fairly nicely distributed. So we'd like that the maximum degree, so this delta 1 is the maximum degree of a vertex, to be only a constant factor bigger than the average degree. And we'd also like for every pair of vertices not to be in too many of the triples. Okay, so it turns out that the right thing to do is constant root d. Okay, so it's a fairly large class of hypergraphs that are fairly nicely behaved. There's not too much bunching up of the edges. Sorry, and this is the definition of delta 2. So we're going to find a collection of subsets of the vertices, not too many. So number of vertices, choose number of vertices over root d. Turns out to be what you get. So with the following 2 nice properties, the independent sets, that is the sets with no edges, are covered by these containers. So you should think of these collection C as being containers for the independent sets in this hypergraph. And none of them are too big. So at least 1 minus delta proportion of everything. This looks like a much more general but much weaker statement than the previous one, and it is. But it turns out that by iterating this statement, so first, you can prove this essentially by induction. So you can really sort of form an algorithm that tells you which sets to take. And because it's very general, this allows the induction to work. And by iterating it, you can prove the previous statement. Sorry, an I of H is the collection of independent sets. So right. So how does it imply the previous statement? Well, it implies it by working on this particular hypergraph, the hypergraph encoding triangles. So applications of the container method, you have a very general statement for hypergraphs. You want to choose a hypergraph to work on. It should encode the problem you're trying to solve. So this one is a very simple hypergraph. It has vertex set the edges of the complete graph, and hyperedges the triples that make a triangle. So triples of edges that form a triangle. And note that the triangle-free graphs are exactly the independent sets in this hypergraph. So this encodes the problem we're trying to look at in a very natural way. We're trying to understand the triangle-free graphs, encode them as independent sets of this hypergraph. This hypergraph has these nice properties. The edges are well distributed. And so just applying the lemma to this hypergraph gives this container lemma, which looks a lot like the kind of theorem I wrote on the previous slide. So it's a fairly small family, roughly the size we want. We cover all of the triangle-free graphs. But now, instead of having little ON's cubed triangles, all I know is I have 1 minus delta times n choose 2 edges, which is not so great. It's not a very strong result. But what can we then say? Well, if for each graph in our collection, either it has little ON cubed triangles, so we're happy, or it doesn't, and then we can reapply the container lemma to it. That takes a tiny bit of checking to gain another factor of 1 minus delta, and just keep going, and after a bounded number of steps, you're happy. So you just apply it a bounded number of times, and you end up with what you want. So again, it's actually very simple. Okay. So, right, so my final slide before we swap over. So I'd like to just state the general hypergraph container lemma for k uniform hypergraphs. The statement is very similar to the one we had before, but it's a tiny bit more technical. So for every k and every c, there's a delta such that now we have a k uniform hypergraph. So now the hyperedges are just of size k. So we have n vertices and a bunch of sets of size k. And now, instead of having just these two conditions on the degrees and the degrees of pairs, we have a condition on the degrees of L sets for all sets of size L. This is just saying the edges are not bunched up anywhere too much. This is saying on any set of L vertices, you don't get too many more edges than you expect. And you can measure this using this tau. Okay, so it's just some condition saying the edges are fairly nicely distributed, and this turns out this normally gives the correct dependence. So now we're going to find this collection C of containers with the following properties. So now I just want to say something a little bit, this just tells you a tiny bit about the proof. So how do you construct these containers? So remember, for each independent set, we want a container, and we don't want too many of them. So what we do is, for each independent set, we find a subset called a fingerprint, which is small, and which tells you that some of the elements are not in your independent set. So this fingerprint determines the container. Because the fingerprint is small, there can't be too many of them, just because there aren't very many small sets. So that tells you there aren't too many containers, because the fingerprint determines the container. Okay. So this is all this is saying. There's a subset, the fingerprint, small, and the independent set is contained in f of s, so the container that only depends on s. And also, the container is not too large, size 1 minus delta times everything. So this is the general container lemma. So perhaps I'll leave this up so you can stare at it for a while I swap over with Yoshi.
Sorry, while swapping over, let me say a few words about our second lecturer, József Balogh, who is an outstanding Hungarian-American mathematician, again working on extremal and probabilistic combinatorics, mostly on random graphs, random hypergraphs, and extremal hypergraph theory, bootstrap percolation, and several other fields. He's from the University of Illinois in Urbana-Champaign, where he has been for quite a few years. Although he got his PhD only in 2001, he has close to 150 papers. I also would like to mention that the topic of today's lecture, the joint lecture, is exactly this hypergraph container is the one for which the two of them, together with Samoti, Wojtek Samoti and Andrew Thomason and Sexton, were awarded the 2016 POIA Prize. So, please welcome in a moment József Balogh, who will deliver the second half, all about applying the hypergraph container lemma.
So in the second half of the talk, I try to give 3 applications of the method. I try to differ from graph theory, and also I try to explain that we need additional ideas to apply or to get the final results. So the first application is in the problem of Cameron and Erdős on the number of maximal sum-free subsets of integers. The second problem is again about by Cameron and Erdős on the number of k-term arithmetic progression-free subsets of integers. And the third topic is on a problem of Erdős from discrete geometry, where we are proving the existence of a finite point set in the plane with some special properties, that they don't contain 4 points in a line, and it doesn't have a large subset in general positions. So let me start with an easy exercise. What is the maximum number of integers from the subset of integers 1 up to n, which doesn't contain a solution of the equation x plus y is equal to z? Such set is called as a sum-free set, and it's easy to come up with large sets without a sum. For example, the set of odd integers is sum-free because the sum of 2 odd integers is even. Another example could be that we take a long interval where the smallest element of the interval is larger than half of the largest element of the interval. This is again sum-free. And if we take the largest possible interval, then we get a very large sum-free set. And it's a 1-minute exercise to prove that these two sets are among the largest sum-free sets. One can think that how to generate many sum-free sets, and the cheap solution is that take a large sum-free set, and all of those subsets are sum-free, and we can generate many sum-free sets. These examples and this observation led Cameron and Erdős to propose the following question: that is it true that the number of sum-free subsets of the integers 1 up to n is about the one that I explained here, constant times 2 to the n-half? This conjecture was solved by Green and Shapozenko independently, and they proved more than it was asked for. They proved the existence of 2 constants, that the number of sum-free subsets is about this constant times 2 to the n-half, where the choice of the constant depends on the parity of n. And if you look back for the example, then it's clear that the parity of n matters, because the number of odd integers up to n could be n-half or n minus 1 over 2, depending on the parity of n. Most of these sum-free subsets are created by taking a large sum-free subset and having all of their subsets. And the second question of Cameron and Erdős was that is it true that the number of maximal sum-free subsets are significantly fewer than the number of sum-free sets? And as a lower bound, they constructed 2 to the n quatermany maximal sum-free subsets. Their construction was the following, that fix a number n quarter to be included in these sets, and have a subset of the large integers from the interval n½ to n, and for every s, include in this set t exactly one of s and s plus n quarter. Then this set is sum-free, and each of them is subset of a different maximal sum-free subsets. And we have two choices for each s, and the number of choices for s is n quarter, hence we get this as a lower bound. And the conjecture was in this form solved by Buchek and Schoen, and the upper bound was greatly improved by Wolfowitz. And using the container method, we settled this problem. We proved the existence of 4 constants that, depending on the 4th remainder of n, the number of maximal sum-free subsets is about 1 of the constant times 2 to the n quarter. We try to explain some of the ideas of the proof. So it starts that in order to apply the hypergraph container theorem, we define a hypergraph. The vertex set of the hypergraph is the set of integers 1 up to n, and we will define a 3 uniform hypergraph, and the hyperedges are triples which are forming a sum. In this hypergraph, the independent sets are the same as the sum-free sets. So if we apply the container theorem, and it's an interesting historical remark that this theorem, just only for this particular hypergraph, was known by Green and Ruja in 2 different papers, and they used Fourier methods to prove this lemma. So the statement is that there are sub-exponential many sets. Each of them contains sub-quadratic many sums, such that each sum-free set is a subset of some of them. And the other tool that we are using is Green's removal lemma for sum-free sets, which says that if a subset of integers contains subquadratic many sums, then sublinear many elements can be removed to obtain a sum-free set. So looking that we obtain containers with subquadratic many sums, then we can apply this removal lemma for the containers, and it means that they are similar to large sum-free sets. Using a stability theorem of Deschler, Freim, and Shoshem-Temkin, who characterize large sum-free sets, we have a characterization of large containers. And then with some more arguments, we managed to reduce the 2 to the little o n function just to 2. We proved that there exist 2 sets. One of them is the set of odd numbers. The other is the set of large numbers, but the large doesn't start from n½ it starts from 0, 4, 7, such that almost all maximal sum-free set has all but 1 element in these sets, one of the 2 sets. And using heavy tools of Green and Morris and lemma of Huiter and Tuzon maximal independent sets in graph, we could finish up the proof of the main theorem. So here again the main starting point was that we could capture the structure of sum-free sets, or most sum-free sets, with the container lemma. The second application is on arithmetic progression free sets. So we used the notation that A, P, and K is the maximum size of a subset of integers 1 up to n, which doesn't contain a k-term arithmetic progression. And Semerey's celebrated theorem is that for every k fixed integer, as n is going to infinity, this APNK function is sublinear. There are many efforts to get more precise values for this function, including Barron's construction and rank invariance of his construction, which is proving the lower bound on this function APNK, stating that the lower bound is almost linear. This is a reasonably small function, and Gauer's deep result, which gave a strong quantitative upper bound on APNK. So the question of Cameron and Erdős was that what is the number of KAP-free subsets of integers? And the reason that this question is not that easy is that we actually don't know this function. The bounds are reasonably close to each other, but not very close. An easy answer is that what Semeredis theorem implies, that there are at most 2 to the little n such sets, but they were asking if the exponent is about this APNK or at least within a constant factor of this APNK. And what with Liu and Sharifzadeh we proved that the number of KAP-free sets is 2 to the constant times APNK for infinitely many n. And the starting point for the proof is again that we have to construct a hypergraph. The vertex set of the hypergraph is the numbers 1 up to n, and we construct a k-uniform hypergraph where the hyperedges are k-tuple of numbers which form a k-term arithmetic progression. Here again the independent sets are the KAP-free subsets, and a straightforward application of the container lemma gives the upper bound that the number of such sets is upper bounded by the number of containers times the maximum size of a container, 2 to the maximum size of a container, because this is the number of subsets of a container. The lemma gives that the number of containers is small. So what remains is to give an upper bound on the maximum size of a container. And if we use a more advanced version of the container theorem, then we can gain the information that each container contains n times polylog many KAPs. So that's the information that we should use to give a good upper bound on the size of a container set. If we go back in the literature, then Warnevides' result, which was actually earlier than Semeredis' theorem, so he proved, assuming that Semeredis' theorem true, that if you have a linear size set, then it contains quadratic many k-term arithmetic progressions. This instantly implies the, for us, useless fact that the maximum size of a container is sublinear. And what we actually prove that for infinite many n, it is true that arbitrary set containing n times log 10 n KAPs has size larger than 1,000 times the extremal function. And that implies the theorem. And the question remained, and it's probably not that easy, to prove the same statement for every n, or it would be even nicer to get the sharp or potentially sharp bound that having many KAPs yields that A must be larger than just the order of magnitude of the extremal function. And the reason that this problem is hard, that actually we don't know what is AP and K. And not only that we don't know what is AP and K, but we don't even know if it reaches both the lower and upper bound infinite many often, and even it could be that the oscillation is too rapid. So here we have just this partial result. The third application is on the problem of Erdős. The years here means that in the mid-80s he published this conjecture multiple times in his papers. So the question is the following. So let S be a point set in the plane, satisfying that there are no 4 points in a line. And we define the function alpha S to be the largest subset of S in general position, so without having 3 points in a line. And we define alpha N to be the minimum alpha S, where S is ranging through all point set of size N having these properties. So Erdős, when posted this question, said that he couldn't prove, despite efforts, sublinear upper bound, or he couldn't improve the trivial lower bound root n, which can be obtained by the greedy method. It was Füredi who improved both bounds. He improved the lower bound from root n to square root of n log n, where he used deep theorems of Komlós-Pince and Szemerédi, the way how Phelps and Rödül stated, and he proved the sublinear upper bound using the density Hell-Jewett theorem by Fürstenberg and Katzelson. And he noted in his paper that the upper bound should be close to be the true, because it's very hard to realize point sets in the plane with such properties. With Solymosi, we actually proved that the truth must be closer to the middle of the lower and the upper bound. We proved that alpha n is bounded by n to the 5 over 6. And again, we use the hypergraph approach. So assume that given n point in a plane, we form a 3 uniform hypergraph. And the vertex set is the set of the points, and the edge set is the collinear 3 tuples. So the independent sets in this hypergraph are points in general position. And actually, this is how Füredi obtained his lower bound, because he considered this hypergraph approach, and then he used some property of this point set and observed that Komlós-Pince and Szemerédi proved that the independence number of hypergraphs with this property is at least this root n log n. For the upper bound, we need to have a construction which has the required properties, and for this we consider the 3-dimensional integer grid. So we set up m the way that m squared is about n, and then we sparsed this point set. We kept with probability p each point, where p is about 1 over m, and then we calculated the expected number of points, which is just p times m cubed, and the expected number of collinear 4 tuples, and the choice of the parameters let us have that the expected number of points is much larger than the expected number of collinear 4 tuples. So we removed the point from each collinear 4 tuples, so we obtained a system that contained no 4 points in a line. This point system is in the 3-dimensional space, so we could just take a generic projection to the plane which preserves collinearity. So now this point set is in the in the plane. And now is coming the hard part that we have to estimate the maximum size of a subset in general position. And for this we are using some iterated version of the container lemma for 3 uniform hypergraphs. So for this, the vertex set of the hypergraph is all the points, all the m cube points, and the hyperedges are the collinear 3 tuples. So it's again a 3 uniform hypergraph. And after optimizing the parameters, we get some number of containers with the property that every independent set is in some of the containers. The number of containers is not so many. And additionally, we prove that the containers don't contain too many hyperedges, and by supersaturation results, we get that the maximum size of a container is bounded by, let's say, m to the 8 over 3. And now is coming the part that we are using that there are not so many containers. Because when we look a container set and we intersect with the random subset, then we expect the number of points to be p times m to the 8 over 3. So p is 1 over m, so we have size about m to the 5 over 3. But we need this for each of the containers. And now we can get it by using the Chernoff bound, and this is where we are using it. There are not so many of them, so we can apply the Chernoff bound for each of the sets at the same time. And now we are done because an independent set in the random subset of the points is subset of both a container and a random subset. So the size of the independent set is bounded by m to the 5 over 3. And now if we put together the picture, we have about m square points having the property that every n to the 5 over 6 of them has a collinear 3 tuples, and that's practically the entire proof. This might sound simple, but there are hard things behind. For example, here I just repeat what we proved, and then I compare it with the lower bound from Furedi's result, which is about n to the 1/2. And from this construction, actually, we expect that just this construction, what I explained, should give an upper bound n to the 3/4, not n to the 5 over 6. So it's a future challenge to improve the result. And actually, we are brave enough. We think that this construction that we explained should be close to be best possible. So now the next step is to improve the lower bound. And I would like to say just a remark that what is missing to prove the sharp bound. So the current supersaturation, which helped us to bound the size of a container, is coming from the following statement. If we have a subset of the grid whose size is n to the 3 minus s for some small constant s, then it contains at least n to the 6 minus 4s collinear 3 tuples. And it could be that the truth is not n to the 6 minus 4s, but n to the 6 minus 3s. And if we could prove this, that this is the correct function, then we would get automatically this n to the 3/4 and hopefully sharp bound from above. So let me try to summarize the talk. So there are about 30 applications of the container methods. Many of them are explained in or at least cited in our survey paper. And many of the applications are counting discrete structures, not only graphs, but for example, the number of ways to color graphs, or there are a couple of applications in probabilistic combinatorics, and not just in the form how Rob explained, but there are surprising papers of Friedgut, Hahn, Persson, and Schacht and Schulenburg, where they used in a non-trivial way the container lemma to establish sharp threshold of graph properties, or properties of combinatorial structures. And there are a couple of papers which are proving the existence of some combinatorial structures. Here, along this line was this discrete geometry example. And we believe that there will be future applications, and we need more work. For example, our container lemma statement is very general, and we think that for particular applications, for particular hypergraphs, we might prove sharper versions or better versions. There are papers which did in the past this, or I complained twice about that the supersaturation results are not sufficiently strong, and there are very strong papers which are proving significant results and boosting the application of the method. And I think that we need many more ideas, that we open the horizon, not close the topic. Thanks.
Thank you very much for the very interesting and stimulating talk. Are there any questions? Yes? Yes.
For the question on collinear triples, you said that the supersaturation you needed was just about the number. There's no condition on the degree of the hypergraph of collinear triples?
Sorry, I didn't get the first part.
So often when you need supersaturation, you need not just the number, but some balance condition, which says that you're not just using the same point the same number of times, but you don't need that for your application.
We need more conditions. I just didn't want to be very technical here. So we need more conditions.
Sorry, any more questions? Yeah, in the background. But I think the questions can be addressed to both lecturers, of course.
Do you know if it's possible to prove a stronger form of the hypergraph container lemma, in which k, which is the size of the hyperedges, is not a fixed constant, but grows with the size of the hypergraph? In this case, we could study not only fixed graphs, but Hamiltonian cycles and such things.
So we have an ongoing work with joint with Wojtek Samotty, where the uniformicity of the hypergraph is going as a function of n, but not as the size of Hamilton cycle, because for Hamilton cycle you would need root n uniformicity. We are in the logarithmic range.
Any more questions from the floor? In that case, may I just ask what you can tell us about not the 3-4 problem, but the 520 problem, KL problem?
So, if you repeat the same proof, then you can get a improvement in the exponent compared to the trivial bound. We didn't write down the details because it looks very similar, but we haven't seen new ideas to.
But do you have conjectures for all pairs KL?
No. Even this 3/4 is brave conjecture.
Very tentative conjecture.
But I'm relaxed that nobody will solve it in the next couple of years. So.
Okay. If there are no more questions, then let us thank the speakers for their wonderful talks.